Just start.
Okay, so good morning to everybody. This is the last, the closing day, fourth day, second international winter course and workshop on neuroimaging that is focused on brain connectivity and mental health. So the work of today is focusing on the foundations of imaging and especially 3D slicer. 3D slicer was a major focus of the workshop that was going on in parallel, and with the motivation, let's say, and the objective is how to use a high precision instrument for 3D visualization in neuroimaging and imaging in general, in the entire body, in the medical schools, and with neuroimaging. It's the only it's the only instrument that currently is national worldwide and can do high precision manual, automated or semi-automated methodologies and work with structure. And it's used widely in neurosurgery or surgery in the body, and also for segmentation, neuroimaging, cartography, and any other application. So you will see today developers talking about it, the importance for neuroimaging, and the presenters will be CF West, Juan Ruiz Alfaro, who will explain how this whole technology can be and is important to be distributed in developed countries and underdeveloped countries for in the medical schools and the hospitals, and also in research facilities. Ron Kikinis from Harvard is the developer, along with Steve Piper, and the founders of the 3D slicer. He will give his presentation of the philosophy and the whole thing, the strategy and the importance of that tool and its history. And then Zora Kikinis from Harvard, she will talk about diffusion MRI photography using 3D slicer. The first speaker will be Nikos Makis, that's me, and I will talk about brain connectivity in imaging, and you will see also how 3D slicer can work very nicely with all these complex procedures. So with no more delay for introduction, I will go in the first talk, and these are my disclosures and my funding. And the first thing I will do, why is visualization so important? Let's think general. And when I think about visualization in science, the first thing that comes to my mind is the double helix. So can you visualize what I am showing?
To share the screen.
Are we sure you are seeing what I am saying?
No. No, you need to share your screen.
So please let me know. Okay, so
put it on in presentation mode. I think
you do that.
Okay, now we are.
Okay. Thank you, Juan. So first thing comes to mind is double helix. And somebody could say, well, it's a thing to think of a double helix. No, it was a tremendously difficult time to get this kind of idea. And there is a story that Jimmy Watson wrote an entire little book on titled Double Helix, where he explains the whole story, the whole history of the thing. So this is what the spectators were showing at the time, and that's how they cracked really the, the visualization of mathematics in Cambridge. And this is a little bit the story with Rosalind Franklin, that they gave them this data from the lab where she was working. And finally, they made this amazing model. At the same time, the line Pauling, a very prominent scientist and Nobel Prize winner, had thought of the DNA as made up of three helices. So another interesting example for visualizations is the dream that Kekulé, a chemist, in the 130 years ago, and he came up with the aromatic rings. So the benzene, he dreamed of a snake biting its own tail.
So, excuse me, we need to stop the presentation and start again, because the software is not reacting properly.
So nothing was.
It was.
In YouTube.
Did you press on this one?
This one?
No.
Okay. So I apologize for this this happening, but at the same time, the CF may be very happy because I am the beta tester. So the second example is Kekulé for visualization, and the third one, the most puzzling in my mind, is this one here of Sir Fraser Stoddard, who is a physical chemist, and he came up with the synthesis of the boromium boromate. And so it's in synthetic chemistry, and this is the configuration. The 3D visualization is very difficult because these rings basically have a very, very difficult topology. And in a conference, I happened to be in a conference of this kind of crew of physical chemists. By accident, they asked him to give a talk in neuroscience, and I asked the Professor Stoddard, how was important color for him in science? Color, that was a specific thing. And he started talking, inspired, because really it was extremely important for him how to put the colors on the three rings, so in RGB. So in our field, in diffusion imaging, for example, it is extremely important also, the color. And it's not just to make good pictures, it's because you have 3 dimensions and you have to color each one of the 3 dimensions. In neuroanatomy, more specifically connectivity, currently it's happening something that is extremely important and really raises the attention to how it will be the field probably in the next be evolving in the next 30 years. And here is a paper of 2015 of the group of Jeff Lichtman at Harvard University, where he, with a new technique, he took a little sample of tissue of a rat somatosensory cortex of the size of 0.13 millimeter cube of a volume, and he sliced it in 2,250 sections, each one of them 29 nanometers thick. That tells us that already what it was done with electron microscopy now can be done also with other techniques. And we, as people that work with imaging and neuroimaging in particular, we have to think about it, because this kind of research is guiding us, is driving towards a different scale of things. Right now, MRI in dead tissue has gotten to 50 microcube, 30 microcube, but not below the micron level. here what it tells us, and Lichtman has made that very clear, is that in the next 30 years, it could be that the entire connectome of the brain could have been solved with these new techniques at the level of the synapses, as you see here, of the dendrites of the individual axons, and basically at the nanoscale level, which is absolutely amazing. So the question that he had, and he writes in his paper, is all that merely descriptive? Does it have any meaning, or it's just for good pictures, nice colors, etc., etc.? And he says that, listen, there was a dogma in neuroanatomy since many years that, excuse me, Juan, I have an issue again here with the program. I clicked hide because it was hiding my thing, something, and okay, thank you very much. Sorry about that again. And yeah, I got it. It's here. Excuse me, Juan, it's something wrong here.
PowerPoint.
Do you know how to do that?
Okay, here.
Okay. Yes. So, so basically, to make it short, the idea is that there was a dogma that when you had two cells that were an axon and a cell body that were very close, it was considered for decades that it's proximity that makes the connection happen. And here, what he comes up with these different visualizations is that it's not proximity, it's the identity of the neurons. They can be very close and they may not have any relationship, for example. And therefore, it's a very meaningful thing, this kind of understanding. And visualizations are extremely important. So visualization is essential and of great consequence to help us focus on external world objects and ideas. It's like when you visualize with a telescope a planet or a galaxy. Visualization is extremely important. We are visual beings, the humans, to help us understand and achieve clarity. Also for the structure of the brain and to assist us in formulating novel hypotheses and advanced knowledge. And basically, I will stop here for the sake of time, this was a long presentation that's becoming very short actually. And this is the importance of 3D slicer because, for example, for neuromodulation, that was the topic of an entire day in this course on Friday, when you have to engage with a specific target where you stimulate, for example, here it's the dorsolateral prefrontal cortex, middle frontal gyrus, it's not so easy because to say that for sure with standard coordinates you will stimulate there because of the variability in the heteromodal association cortices in humans. So when you have the individual brain and you use a tool like 3D slicer manually, you can be extremely accurate and precise. If you do automation, you will be quite, let's say, you will have, because of the variability and the automation processes, you will be almost precise and accurate, but not as if you do it with manual editing. And this is the possibility that 3D slicer provides. And I would like just to tell you that this is the CMA team, Center for Morphometric Analysis, and there was created in the 90s the Harvard-Oxford Atlas, which is widely used by David Kennedy and Vern Cavines, and this is the Harvard-Oxford Atlas on the left. It was the fMRI experiment came from there with Jack Bellibon from the center and David Kennedy, who did actually also this picture. You see visualization, how important it is. This is the head in reconstructed with MRI technology in 1991 of the first technician of RA of our lab. And this is currently what is the CMA with Jared Erasmus, who's leading the neuroanatomy effort, Yogi Zarathi, the tractography and the core, and Mark Kubicki, who basically will replace me. And thank you so much for these visualizations, especially the 3D slicer, Ron and Steve Pike. So the next speaker is Carl Friedrich Westin from Harvard Medical School, and he will talk about what is the future then of the MRI.
You have to stop sharing or maybe I can this works out. Okay. All right, thank you, Nikos. Nice.
Like this?
Yes.
Okay. Can find. Okay, good. Yes, so you saw many like high-end advanced images from Nico's talk. So I'm going to talk a little bit about what kind of hardware you need to get to this kind of high-resolution imaging, and especially three things I'm going to talk about. First, why you need high gradient strength and high slew rate. And high slew rate means how fast you can ramp up to that gradient strength you want. You really need this to do kind of modern microstructure imaging. Another thing I'm going to talk about is the trend from normal MRI scanners, like full body. The trend is to move to head-only scanners to get even more, even high resolution imaging, because now the hardware is not limiting us anymore. It's actually the nerve stimulation. So I'm going to talk about that too also. So we have to move to head-only scanners. And then the last thing that is also an exciting trend is that we have had open source software in many domains, but for MRI scanners have been a closed system. So, but the past 2 years now, people are developing open source software and can share them, and that will make all the developments much faster and robust. So just a few words about microstructure imaging, and we mostly, to see things that are at cellular size, we need to use diffusion MRI. We're really probing how the water molecules are bouncing around and hitting cell membranes and looking at statistics of those motions. And it's kind of indirect to do in vivo histology. I mean, it's amazing how this field had moved on for the past 20 years. And this is the technique we use to do tractography and look at white matter tracts, etc. So the reason we want strong gradients is that the measurements that we do require a certain amount of diffusion encoding. And one popular variable is called the B value. And the B value is kind of, so we see like the area under those, the gray area here in this sequence diagram. But as in most sequence MRI, you have an exponential decay when you do the measurement. So the longer you wait, the more signal disappears. So if you have to do very strong division encoding, you have to wait a long time, and then you don't have any signal left. So, but instead having like the lower one, very strong gradients, you can do the experiment faster, and then you can then get a much higher signal to noise. A second advantage of doing strong gradient is that you're actually looking at smaller scales, so smaller spatial scales. So if you want to look at white matter tracks, that white matter axon is normally like 1 to 2 microns or less, and with the top sequence there, you will get looking at much larger scales. So this was all known over 10 years ago, but we didn't have the hardware. And the first kind of, they call it the connecton scanner that was designed to look at white matter tract was installed at Mass General Hospital in 2011. And it was really an amazing kind of engineering effort to get this together. You need a lot of advanced gradient coils and also a lot of power. This Connecton 1 scanner, as we call it now, had 24 megawatt peak power, which is an amazing amount of power. I mean, compared to like a nuclear submarine is about the same peak power, and compared to a normal MRI scanner, it's only 1 megawatt. So it's like 25 times bigger than a normal scanner. So even if you had those machines, and you have to connect it to the outlet in a hospital, it will be complicated. This was supposed to be a one-off machine, but other groups kind of persuaded Siemens to build 3 more. So Cardiff got one in 2016, and also Max Planck, Germany, and then Fudan, China, got one in 2018. So, and they're all running, and they're producing nice images. And an example of what you can do with these machines, you can actually get very high resolution. This is 0.5 millimeter isotropic resolution. You can see then, even in the gray matter, the organization of the different cells. In vivo, you can do also very high resolution. The lower right one is 2 millimeter cube, which is kind of very difficult to look at U fibers. But if you go to 0.67, you can get a lot more resolution, and you can find more information in this paper with Yogesh Rathi as a senior author. There is actually a clinical kind of version of this Connecton 1 now that was released. I think the first one was installed now in mid 23, and some are now being installed in 24. So this is not exactly, it's 200 millitesla instead of 300 millitesla, but it's very close to the Connecton scanner, and it has slightly less power requirement, but still it needs a lot of power. But to go further, I mean, they try to figure out a way how to reduce the power, and also to reduce this nerve stimulation, PNS, which really limits what you can do on these scanners. Now we have enough gradient strength on them, but we cannot use them because of the nerve stimulation. So that's why we come to this head-only MRI scanners, and Connecton 2 was something developed by Siemens, and it was installed this year, and the first images was from July 2023, so really recent developments. So then you can go up to 500 millitesla instead of 300, and much higher slew rates, so 600. And they've developed new coils for this, and so this is a head-only system. You can see the bore is much smaller than a normal magnet. And here's a paper with Susie Wang as the first author, and Bruce Rosen last, describing this system, and it was many years in development. They also did a study how this nerve stimulation affects, and it's here's a simplified version of this. And basically what happens, if you want to slew very fast, you cannot have a large gradient, and if you have a large gradient, you cannot slew very fast. So you can do either or, and in the middle there you have this nerve stimulation limitation, and you really have to be careful when you have these kind of very super strong gradients, what you can do. And another head-only scanner is from GE. It's called the Magnus, and Magnus stands for Microstructure Anatomy Gradient for Neuroimaging with Ultrafast Scanning. So what they did, they took a regular GE Premier scanner. You have the gradient system on the left there, and they removed that system and put in this Magnus system. So it fits in a Premier scanner, but then after you put it, you only have 42 centimeter bore size. And this system has 300 millitesla, so almost the same as the Connecton 2, a little bit lower, but it has higher slew rates, 850 instead of 600 compared to the. So the first system like this was installed in Walter Reed, and you can see like the schematics here on the top right. So and it looks pretty tight, but if it doesn't feel as claustrophobic as it looks, because you have a lot of space for your arms and the shoulders.
No.
Okay.
Yes.
So maybe because when they reconnected, okay. Okay. And now back to the PowerPoint. So these are some examples of the images we have. The top row is from a regular full body scanner, and from left to right you have different diffusion encoding, and the third one, B1200, is kind of the normal encoding you do on a clinical scanner. And you can see if you go higher after 1200 on the clinical scanner, I mean, you lose a lot of signal, and in the end you don't get anything. With the Magnus system, you see you can go almost up to 10,000 and still have very good signal. And that means that you can then look at much smaller things and get more resolution in all your diffusion measurements. And also this very short, the quick slew rate, as I mentioned, we can do shorter echo spacing, and that reduces the distortion. So you can compare. On the top, you have much shorter echo spacing, and then you see you have less distortion. So this system is not only good for looking at diffusion MRI, but all sequences will benefit with this very fast ramping. We got our system installed actually this December. It was in the middle of the night. This is outside the Brigham Women's Hospital in Boston, and it was an interesting to see how they managed to move this very, very heavy magnet into this small hole in the wall that they opened, and they had small wheels that they were kind of pushing it through here. So I was very impressed by how they could move this heavy magnet. And then in the end, it's installed now. So what's happening now, we're currently waiting for the gradients to be installed. So this is only the magnet part, and it will be up and running probably end of this month. Just a quick thing about the open source, that this is another exciting development that I mentioned. It's called PulseSec, and there is a link in the corner to the GitHub. And it's a collaboration with many labs here. And the idea is that you develop in MATLAB or in Python. And there are examples on GitHub on several kind of standard sequences, and more are coming. That is then compiled or kind of translated into kind of something called a sec file. And then you have specialized interpreters, Siemens and GE, and there's also a Philips one, and they're working on Bruker, so preclinical scanners. So you can use the same code for all the different scanners, and there are more than one reason to do this. I mean, if you want to do a multi-site study, you kind of want to have the same code running on all the scanners because they all have slightly different features. But maybe the most important part is that it's much faster to develop in this way. A good postdoc or student normally takes 1 year to get familiar with the code for Siemens or GE, and it's only productive kind of year 2. With this type of system, you can get up and running in maybe in a month instead. So you're saving a lot of time as a student, and also projects are saving a lot of time for faster development. So currently there are mostly scanning phantoms, but we'll soon apply it to clinical studies. So here's a few papers about for more information. So just a quick summary. As I mentioned, high gradient strength is important to get signal enough to look at small things like white matter tracts. Currently, nerve stimulation is now limiting factor, not the kind of quality of the hardware, and that means we have to go to head-only gradients to push the system to what they can do. We just got our MRI scanner delivered, but it's not completely installed. But in a couple of weeks, we'll get the first images, and I'm extremely excited actually to to see what we can do with that machine. And also see what Martino Center is doing with the Connectome 2, and we can compare and learn from each other. And the last thing, the open source MRI, I mean, this is going to change the way we work dramatically, and allow for much faster prototyping and also sharing. Sharing has been a very complicated thing because you're not allowed to give out source code from because of the vendors. So now we can actually even send or put in GitHub new development. So that last one is extremely important for collaboration and how to move forward. So I stop there. Thank you.
So are there any questions for CF Westin?
Yeah, I have one.
Okay.
I mean, this sharing, it sounds very good, but how similar will it be in the actual machine? I mean, you have a lot of bricks for there. So how similar will it actually be, even if you run the same code?
So it will not be exactly the same because the hardware is slightly different, but at least it will be more similar than today. Because, as you say, they have all these tricks, but now we're bypassing some of those tricks. Because also in the reconstruction, those methods, at least they will be the same. So, and I think they've done some tests comparing, and they get much less variation between scanners with this. So it's not perfect, but it's much better.
And for sure, it's much more friendly for the people that are undergoing the MRI scanner because the form of the
Oh, you mean the head-only scanner?
Yeah.
Yeah.
It's extremely important in clinical practice.
Yeah.
So is there another question? I have one comment, not one question. Now, this is a very important talk by Professor Westin, especially for the recording that will be heard after listened by the local people at the University of La Laguna, especially the MRI people, Jose Luis Mora, and also the Institute of Neuroscience, Alberto Dominguez, that they can start thinking of how is the technology evolving towards better spatial resolution, and especially to do experiments of a different kind. So they should
Okay.
Okay, so
Separate package.
just the last 2 seconds,
Yeah.
we lost audio the last 2 seconds.
That's okay. So, especially to start thinking of the talk of CF Westin and also the next one of Juan Alcola, so that they realize what is the range of possibilities from something a center that is in a country like in Africa, let's say Mauritania, because this is a reality. One is promoting technology in this underdeveloped countries or underdevelopment. And here in the Mediterranean area, like Spain, Italy, and Greece, because I'm Greek and I know how is in Greece the technology and science. In comparison with the very developed countries like Northern Europe, or Sweden, from where CF Westin is, and the United States of America, especially at Harvard, where we work. So it is important to realize all these things and get into contact with the people that are in this winter conference, because this is one of the major missions of these meetings, is how the technology that we develop over there, because you see developers here that are coming. How do you contact them and get this opportunity really to make work a little bit better the system? Okay, so this is it may be a long process because last year there was some participation from the local university. This year it was a little bit more, and I hope that slowly, but not too slowly, because we're getting in retirement, several of us, you would just cheer up and participate in this presentation as well. Let's go to the next. Yes, please.
Thank you very much for the really nice, interesting study. So, how is the develop? It was not very clear to me. How is the development divided between the company and the Harvard MG? So, uh, the coil, the gradient coil design part, the electronics part. How is that arranged to obtain the scanner? Yeah.
So I think the development of the Connecton 2 scanner was very closely done, Siemens and the Martino Center, because they had a long relation building the Connecton 1. For the magnet system from GE, that had been mostly developed in-house. So we have not been part of that. So we want to be more a part of doing new software and fancy sequences that can take care of that. And then using these open source is one way, not the only way, but we want one way we want to do it. So there are two different models. I mean,
Yeah.
So we are in good time now. Yes, for one. Right.
And then I just share the screen, right?
Yes, we can hear you perfectly.
And now I can change my whole screen. That will be easy. I cannot share.
Or window.
But then if I change if window, but then so I cannot.
Which window?
Okay. No, I'm sharing the whole screen.
By the way, everyone who is not present should turn off the video because we can we should that's a very afternoon.
When you record everything, okay? Yes. Recordings are the most important thing.
Should I start?
Whatever you want.
Okay. Thank you. Thank you, Nico, and thank you all for this kind invitation to talk today. So, I mean, I try to. I'm not sure what content should I provide, what type of presentation I should do, since I mean I'm not a neuroscientist and I haven't been working, for example, with MRI for some time for some time now. So my experience, I believe that what might fit this workshop is on one hand side. I mean, on one side, it is I started working in the SPL at Harvard 25 years ago, and somehow we managed to keep the collaboration across 2.5 decades. And since I think that Unicos are interested also in trying to foster collaboration and bringing up new projects and opportunities. I mean, I think that we have been successful at keeping a collaboration for many years now, and within this collaboration, many people have participated. So first of all, of course, all people developing Slicer and all the international community. And 5 years ago, we started to play also an additional role as we were hosting NAMIC Project Week events. We have just had the last one in Las Palmas, so it usually alternates every 6 months with a location in North America, usually the MIT, and then since 2018 in Las Palmas. And I think this is very important for us because it gives us the opportunity to play a role within the international community and to provide something. And the thing that we are providing, I think it is giving opportunities for additional connections and additional collaboration. And this is where the developing countries appear. So we have been working with them, with several Western African countries, at least since 2016. And yes, we have had several projects with them, and those projects have also being leveraged by colleagues, and now they are ongoing direct collaboration between these African countries and institutions in North America and Europe that somehow started through our previous collaboration. So that's number two. And number three is that you mentioned before, Nikos, that I also have a laboratory here at the Institute of Astrophysics, and that's a different story. So the Institute of Astrophysics is a world-class institution in its field. It's highly internationalized, and what we have there is a laboratory specialized in doing technology transfer from medical image from astrophysics technology to medical image computing. They might look like very distant fields. They are not. I mean, there are some commonalities and synergies that can be leveraged. So these are the three things that I can explain more. So since the title was making reference to this collaboration with these countries, I'll let you know show something about it. We actually started in 2016, but something that is always necessary. You have to write grants. So because we all need funding, no projects. So in 2015, I think that by the end of 2015, Ron Kikinis came to the Canary Islands, and I'm extremely grateful because he has helped me across my career many times and very much. And this was important because it gave credibility to the project. This helped me show that there were real connections and real opportunities. And well, we started working with Senegal, with Mauritania and Cape Verde. In the case of Senegal, we were working with a main university in the country called Cheikh Anta Diop, and then with the military school of medicine, and also with the main hospital in the country, the hospital FAM. In the case of Mauritania, we are working with the Central Hospital and the University of Nouakchott. In Cape Verde, we are working with the University of Cape Verde. And the thing is that many things started to happen, and I will show you some of them. So these are just pictures from our initial time. You can see here Ron with Professor Dada Lepchir from Mauritania. Here we have Babacar Diaw from Dakar, from Senegal. And for us it was strategic to keep the link with these countries for a number of reasons. So it wasn't easy, to identify what field was useful for them and for us, and in which field we could collaborate. And we decided that clinical simulation for clinical training might be a good match, because training is absolutely needed in these countries, and they need education. That's number one, and number two comes funding, but number one is education. And we had a good opportunity around the slicer. There is this platform called Slicer IGT that was developed by Professor Gabo Fichtzinger, who is here today, and his colleagues at Queen's University, and on top of Slicer. And this proved really useful, because it gives a way, to combine technology and non too sophisticated applications. So we didn't go for clinical applications at the beginning. We went for training. Oh, this is Cape Verde. So all these initiatives started, to make some noise. This is the ambassador of Senegal to Spain visiting our laboratory a few years ago, and his director, the ambassador, with the former ambassador, and they started to pay attention. So, for example, here in Mauritania, and in Senegal, but in this case in Mauritania, this young lady is showing a part of the anatomy atlas that they developed with their own data in Nouakchott. And I mean, and this was challenging because they were starting, from a level that is quite different to ours in terms of resources. Of course, there are smart people there; so they are everywhere. But in terms of resources and organization, there were challenges, and they overcame many of them. So we have been working around different projects. I would say that if you wanna collaborate with these countries, I would say first of all that remember that African countries are now fully eligible in framework program in the EU framework program. So this essentially means that we can have them as partners. That being said, it will be a challenge because these grants, as you know, and these programs are complex, and you require, I mean, you need some administration behind you to support this sort of projects. Something important is that we should address their needs, not ours, and of course at the same time we should build win-win relationships so that it's also interesting for us. So we have done several analyses about what is most needed, try to speak with them, try to discuss. And yes, I mean, this simulation has been clinical simulation is a good opportunity, I believe. There are also clear needs in health information systems. And of course, I mean, this is an imaging conference, and Professor Westing was talking about MRI and modern MRI systems. So this is the data center of a hospital I visited. In this case, it was Mozambique, and in this case, one CT scanner on the right side. So they like essential resources, and I mean, you can imagine the data center, like you can see this in this picture. So I'm gonna skip this because I believe. So in the case of technology, we are using 3D slicer for a number of applications to build or atlases with our African colleagues, I mean, and using their own data. We also developing some clinical simulators for training, and I believe these are the main applications. So here you can see we have been developing systems not only under a slicer, but also using video gaming technology for clinical training. And yes, I mean, I don't think. So developing all these systems provides an opportunity not only to produce the system that you want, but also to learn how to do that. So when we do it with them, they and us, of course, and we all learn together, and they can drive themselves their own challenges. So all of these systems have been developed in collaboration with open source software. I have here an introduction to our new project. It's called the Virtual Hospital. So virtual it is because the patients are simulated. We have standardized patients, that's actors, and also technology patients, so simulated patients using mannequins or using using software. And so this video is a little bit old. This is not the last version. I will show you now on the website. But essentially, what we have is a 700 square meter building that has been donated by the university to the project, and this is an international training setting that we are currently developing. So we are writing grants like crazy, as you can imagine, to get on the resources we need. But I mean, we already have something, and of course, I love to have the opportunity to collaborate with colleagues across the world, and particularly in Europe within EU framework programs, to make things together. As I say, everything is simulated, and we mainly use open source technology, Mature Slicer, of course, but also other systems. And what we are trying to do is we are actually replicating not only a hospital, but a real hospital, but a real society, so that we can address all the challenges that there exist in healthcare, from primary attention, visiting the doctor's office, of course, hospital, all information management, simulating or training surgical procedures. So it goes in many different directions. So this is a big project, and one of the motivations is to offer the project to our African colleagues as a reference, so that they can develop their own training centers in Africa. And for us, of course, it's an opportunity to develop technology and to test new systems before going to clinical research trials. So I think that there are nice opportunities to collaborate within this in this specific area. So now I'm going to show you very quickly a few other things that might be interesting. So I'm sorry, they are not well ordered. It's been a complicated week, but I think that you'll get an idea of what I was telling, what I was saying before. So first of all, NAMIC Project Weeks, I think they are a wonderful opportunity, and we are lucky because we are hosting once a year these Project Weeks, working together in around the slices and other with other technologies as well, using artificial intelligence, of course, slicer, medical image computing, etc. So next one will be now, we just had the 40th edition. So next one will be in Boston in June, and then the next one will be will start January 27, 2025 in Las Palmas. So I think this provides a good opportunity for interaction. You can have an idea of the projects that we have had this more. I think it were like 65 projects. We had 85 in-person participants, or 150 remote, including remote participants. So I think this is a good opportunity. Now we have also. We're trying to put everything under a common umbrella, and we have a website. So I'm not going to go into detail with the website, but I want to show you something, because I think this is something significant. So Professor Babacar Diao joined our project, I think it was 2018 perhaps, and he has been using a slicer for surgical planning, and they didn't know about that. And I'd like not only show you this picture, but show you this video that he recorded explaining how this was for him to perhaps it's gonna be difficult with okay. So he essentially did the two first kidney transplantations in Senegal, and he used 3D slicer and all he had learned in in our projects in collaboration with us, our colleagues, and our international colleagues, so that I mean, he found this like a great help and gave them a confidence to make to start the kidney transplantation program. So this project McGree is the project that we, I mean, it is the main grant that we used for years. So I think this is a clear outcome, and that something are moving in the right direction. And I'm really happy with this, because we didn't ask him to do to make the video. He did it by himself and shared with the community and with us. And another important thing it is, and especially when it comes to many regions, there's a disconnection between industry and research. And this happens here in the Canary Islands, as it happens in many other places. And in our case, what we are trying to do is that we're trying to connect with practical things, including what I said about this African collaboration, but we have also started a spin-off company on using this open source technology. And right now, this little company, university spin-off company, is employing people who, when they finish their grant period at the university, and the thing is that they are developing technology, they're developing new projects as a company and employing some people. So I think this is something that is important for us too, because we have to somehow connect commercial activity, and more than commercial activity, entrepreneurial activity and industrial activity with research. This is, of course, taken perhaps for granted in Massachusetts or in some places in California, but I can tell you this is not the same case here. And for us, it's very important that we advance also in promoting some companies that can somehow leverage the research results and give opportunities to talented people who they finish their period at the university. So that's it. Thank you very much.
Thank you very much. Juan, is there a question for Juan?
Sorry? I should.
Are there questions for Juan? So I have a comment on from some categories yesterday. Actually, yesterday there was Bristol Miami here, the presentation of the PNS, UG, all the technology. And I asked a very concrete question. You can hear it was a discussion for 10 minutes after, exactly on the relationship between academia and companies. So Bristol Miami started a company, and he was in academia, and I asked how, and this was 30, 40 years ago, right? Maybe 40 years ago? No, 30 years ago. So this was exactly the topic of discussion yesterday. It was an extremely important topic of discussion for all the Mediterranean area, not only for Spain. Mm-hmm. And what, for example, in Massachusetts, I remember Mauricio Fava, the director of the Chief Department of Psychiatry at Mass General Hospital, and he used to be a director of all research in Mass General Hospital. We're talking about administering $140 million a year only for research, for billions of dollars for pharmaceutical. How he was advocating for us, the faculty members, to create companies. So they were giving us classes of how to make a startup company, and for a few dollars, let's say, something like that. So they consider it extremely important, the relationship of academia with industry. Extremely important. The academicians will understand how to work in corporate world, and also to create companies. There is a very difficult understanding in my mind of the conflict of interest on that, and that's why I asked, especially Risto, yesterday, what are the conflicts of this kind of relation? And there are many conflicts, and there are many rules that they have established already in these other countries between academia and industry, and it works very, very well. But it is a culture that we don't have in the Mediterranean area, with the result that you have seen that of hostility of academia towards industry. Okay? So I think it's an extremely important topic of discussion. You are in the center of this topic, and by Risto being here and Nubi, who is basically the corporate area, the corporate arm of the computer labs. Yes, so these are things that we are discussing very much, because I think this is a tremendous detail. It's not even a detail, it's a factor of progress.
Yeah.
But there is, so again, as you said, a conflict of interest is one issue. But there is also in general the issue that basically perception. And when an academic stays in academia, but is also commercially active, there's always the danger that it gets misrepresented. And in general, my experience is that academics are, relatively speaking, naive in this type of things that go into politics and other things. And I've seen over my decades in the field, many people who ended up on the front page of the Wall Street Journal or the New York Times or any other journals, not in a good way. And because of this, I think ultimately if you work in biomedical research, going to a point where you have a commercial product is the validation of the research. Because you want to do the research to basically help humankind. The scale up from a small scale research project to something that's available to every patient who needs it is commercial. So there's no question that doing commercial things is important, but how to do it and not to be eaten by the beast in the process is very difficult. And so trying to do both at the same time is even more difficult.
Absolutely, you are right. So we started this experience because not because I want. We did it because grants were over, and then this was the only opportunity to give a chance to the people and to to some of the researchers, and also to the project and the strategy that we had.
And you had to get a law degree.
Yeah, you're right, and I mean, I think we are very bad business people, so we are not trained to do that. So when you are running a business, you have to think in business terms. So, for example, with this, I just have a little share that I'm allowed by the university, because there's you have to manage the conflict of interest. Things have to be clear, open, and we only use open source so that there is no conflict. If the company wants to develop something close, it will be their business, but they will have to pay for that. So that anything we produce at the university is open source and shared. And in fact, the company is also producing a significant amount of open source. So we did it because of need. So we, as I said, we are not really business people. And in fact, my personal position is more emotion. If you are a business person, you shouldn't be emotional. You should just be a business person and investor. Be a business person and investor. So we are trying. So maintain and keep many things alive and many open opportunities. But I'm actually thinking as an academic. I'm not thinking like as a business person. And at some point, that will be a limitation for the company. And I just interested that they start, that they progress, and eventually stay aside, because I'm an academic. I'm not a business person.
I have also one maybe short question. In this presentation, you
showed that so you are working closely collaborating with this slicer. And one of the main uses is educational purposes everywhere, and then the other one that I know this is mostly referred on medicine. Now, my question is, what about neuroscience, neurology applications? What do you see from your coordinate system over there in these countries? Like, is there any stigmatization of the diseases? Is it some kind of unhidden, maybe hidden problem in a way that there is a need, but it's not okay to talk about it? I mean, what's the situation in these countries?
So what I think is that what you said, there's a stigmatization of mental diseases. So in some countries, it is really very complicated, and perhaps there's no. I don't know enough, but I think that in some of these countries, there's not. Mental health is not that real. So I mean, in this case, mental health. If you ask about neuroscience, I think that it's very difficult to involve developing countries.
Yeah, but there is one aspect of the stigmatization of mental illness. Is a huge problem. It is a problem that is not acknowledged by many. But there is another aspect which is neurosurgery. Brain tumors occur everywhere, and there is a need for surgical intervention in many places. And so one of our collaborators, Alexandra Golby, is actually building a neuronavigation system based on a 3D slicer. The project is called NUNAV, and it is being run in clinical trials in Senegal, Morocco, and I think Rwanda right now. So there are activities to make, and again, leveraging the open source in the NUNAV system, which is not CE marked or FDA approved. And special care was given to minimize the requirements for additional hardware and to make the majority of the hardware that is needed can be 3D printed locally, and in particular the supplies, because the supply chains in those countries don't work well if they are present.
This project is very interesting, as Ron explained. So in my view, and I've seen that there with this system, it is a technical skill. So you need some technical skills to make it work properly. And technical skills, for example, to calibrate things. So you need someone has to understand what the calibration is, and not the neurosurgeon. The neurosurgeon wants things to be calibrated, but you need someone who understands how transformations relate to each other and how to do it, why you should do like this and not like that. And I saw, last time that Alex was there, and Gabor didn't come that time, but it was Chava. Chava was there as well. And how they would calibrate, the needles and the stylus. Like, they didn't realize what a pilot calibration was and why the tip had to be steady. And if you don't move the tip, calibration is bad and you lose absolute accuracy. And then, you are using that on a patient. So
We are almost out of time, but I just wanted to make a point, and that's why I was pointing at Gabor, is that Gabor and his people actually traveled multiple times, both to Senegal and to Mauritania, and are hosting people from those countries at Prince University for training in IGT. And exactly what you were describing, how to do the calibration, is one of the big breaking points. For training, you need phantoms, and phantoms can be made even in places like Mauritania, because they are essentially gel with a little bit of color. I mean, I'm simplifying, but not too much. But it can be done. But to get it done is now how many years? Like 3 years, something like that. 3 years sustained effort. We are not quite there yet, but we are making progress.
And we should make a good plan because these practical aspects, so we need them to understand how to calibrate, but not just like a mechanical thing. Some of them should know, should understand the thing so that they can, I mean, solve and lead their own development and handle their own problems. And there's a lack of basic technical knowledge, I would say, and that somehow we have to contribute to improve.
Good. So we are out of time, but we will at the end continue that conversation.
Yeah, so we're going to close with a complete conversation. And now it's,
Now it's my turn.
this would be a magic straw.
But first you have to feed me a sugar. I'm joking.
Well, can you give it to everybody?
No, give it to.
Can we wait 1 minute, please?
Yeah.
To stop the emission and start it again.
So what do? I don't do anything.
It's okay.